Hello and welcome to day 1 of Unit 4. Today we're going to be talking about section 4.1, and today we begin our discussion of analysis. Okay, so the analyzing a function based on what its first and second derivative tell us. Okay, before we do that, let's look at this warm-up. It's a related rates problem. So if the base B of a triangle is increasing at a rate of 3 inches per minute and the height is decreasing at a rate of 3 inches per minute, which of the following must be true about the area A? Is A always increasing? Is A always decreasing? Is A decreasing when B is less than H? Is A decreasing when B is greater than H? Or is A remaining constant? Okay, so the first thing I need to do is set up an equation. Area is equal to 1/2 the base times the height, right? That's the formula for the area of a triangle. And then I'm going to differentiate with respect to time. So I'm just going to use primes to save time here. So A prime is equal to 1/2, okay, the first times the derivative of the second plus the second times the derivative of the first. All right. Okay. Now, H prime is decreasing at a rate of 3 inches. So H prime is -3. And B prime is +3. Okay. So what I'll do is pull out a 3 and move things around. Now we have to assume that H and B are always positive values, right? Because we can't have a negative length for a base or our negative height. So the question is, what is the sign of A prime? Is it positive or negative? That would tell us if the area is increasing or decreasing. Well, it's going to vary. It's going to depend on what B and H are. If B is larger than H, this comes out to be negative, right? And if H is larger than B, then this comes out to be positive. So when B is greater than H, A is decreasing. So the answer here would be D. Okay? It's not always increasing because there are points where this is negative, or excuse me, where this is positive. And it's not always decreasing because there are points where this is negative, positive. And obviously A does not remain constant because B and H are variable. B and H are changing as time goes by. All right, so before we begin, we have to talk about some vocabulary. There's a lot of vocabulary in this section, but a lot of it should be review. So I've sort of grouped all of the vocabulary in colors so that I can demonstrate what the vocabulary is referring to on the graph. So starting with absolute and global max. Two words mean the same thing. All it means is the absolute maximum value of this function. The largest value possible, or excuse me, the largest point possible. Okay. Absolute min, global min, same thing, but for minimum values. Okay. Now, in the case of this graph, there is no absolute min or global min. Okay. Because if you notice that on either end of the graph, it goes to -infinity. And -infinity is not somewhere we can reach. Therefore, we say there is no absolute min or global min. None on this graph. Okay. Maximum and minimum values. Okay. The value refers to the actual f of x value that you get out when you plug in the x to the function. So that would be the maximum value. Again, there is no minimum value. Local and relative max. Local and relative max is any peak. Any peak. So this here is a relative max. So is the absolute max. It's also a relative max. Local and relative minimum. That's any valley. Okay. Extrema. Extrema are any of these two. Any extreme value, maximum or minimum, relative or global. Critical points. Critical points include extrema and changes in concavity. Okay. However, the critical point refers to the x value. Intervals of increasing, decreasing, and intervals of constant change. So increasing would be any interval. So in this case, from negative infinity to C1 is an increasing interval. From C2 to C3 is an increasing interval. Decreasing intervals, C1 to C2, and C3 to negative infinity, or positive infinity. It's not really true. At some point here, there's an x value, not a critical point, but a place where I wanted to demonstrate where the graph could be constant. Which brings me to the last point, intervals of constant change. So that would be from x sub 0 to infinity. Oops. And again, x sub 0, not a critical point, just a point where I wanted to demonstrate that the graph may become constant. Okay. Concavity might be new to you. I think everything up to this point you've seen in pre-calc or algebra 2. Concavity refers to how the graph is curved. So concavity or concave up looks like this, concave down looks like this. So if you make a C for concavity and you're opening down, that's concave down, opening up is concave up. Okay, so this is downward concavity, upward concavity, downward concavity. This right here is upward concavity because it's part of that C and it's opening upward. And this right here is downward concavity. Again, because it's part of the C, it's not the whole C, but it's part of it, and it's curved. The curved part is looking down. And now that we have the vocab straight, let's analyze some functions. Alright, so first up, what I want to do is find intervals of increase, intervals of decrease, and any points of inflection. A point of inflection is where the concavity changes. Let's go back. Alright, so for the first example, I want to find intervals of increase, intervals of decrease, and intervals of concavity, and any point of inflection. A point of inflection is where the concavity changes. Okay? So, To do this, oops, giving it away. Let's think about what a polynomial graph looks like. Okay, it's got these hills and valleys. It's got these peaks and valleys, and the function is increasing from a minimum to a maximum, and decreasing from a maximum to a minimum. Okay, so what I want to find is these critical points, these maximum and minimum values, okay, or where they're happening. That's why we call them critical points. So to do that, I want to know where the first derivative is equal to 0. Well, this factors, well, first of all, I can divide by 6 and then factor and get t plus 1 squared. Okay. And so this is equal to 0 when t is negative 1. So what I'm going to do is make a little number line. Plop negative 1 down there, that's my critical point, and I'm going to examine what's going on either side. Okay, so how about when t is 0? When I plug 0 into here, the derivative is 6, which is positive, which means the graph must be increasing. I'm going to label this number line as f prime. Okay. How about when I plug in negative 2? When I plug in negative 2, I also get 6, which is positive, which indicates that the function is increasing. So there I have my intervals of increase. There are no intervals of decrease. This function is always increasing. Now, there is a debate among mathematicians as to whether or not the function is increasing or decreasing or neither at negative 1. For me, number 1, I'm going to say that it is not increasing nor decreasing at negative 1. So I'm increasing from negative infinity to negative 1 and negative 1 to infinity. There are no intervals of decrease. Okay, now I want to find intervals of concavity. Now this is something new. The second derivative actually tells me about the concavity. The second derivative of a function will tell me whether or not a function is concave up or concave down. It's called the second derivative test. Okay. Where that's equal to 0 is a possible point of inflection. It's not guaranteed to be a point of inflection, but a possible point of inflection. So let's look at what values of t make this true. And again, it's t equals negative 1. So I'm going to make another number line here. Label this one f double prime of t. There's my critical point, or excuse me, possible point of inflection. And I'm going to look at what's happening here, and I'm going to look at what's happening here. Well, when I plug in 0, I get 12, which is positive, which indicates that I am concave up. Okay. When I plug in negative 2, I get negative 12, which is an indication that I'm concave down. Okay. So to answer part 2, I am concave down from negative infinity to negative 1 and concave up from negative 1 to infinity. Now my point of inflection is at negative 1. That's where the concavity changed. We'll do that in a different color. Point of inflection, not interest. That's a T. Equals negative 1. Okay. So what might this graph look like? Well, now I have a decent idea. At negative 1, there's some really interesting things going on. Now I could plug negative 1 into the function and get an actual value. Let's see, it's going to be negative 2 plus 6 minus 6 plus 4, which is plus 2. Okay. And then from negative infinity to negative 1, I'm increasing. And from negative 1 to infinity, I'm still increasing. However, my concavity changes from concave down to concave up. So it looks like a cubic function, but it doesn't have the two hills and valleys. Hills or valleys. It just has one point of inflection. Okay, so now for something a little more interesting. Something that's not like a polynomial function. Something like this. Though this isn't a polynomial function, all the rules from the previous examples still apply. Okay? So I'm going to use the first derivative to find intervals of increase and decrease, and the second derivative to find intervals of concavity. So let's find the first derivative is first times the derivative of the second plus the second times the derivative of the first. Okay? Now that factors out nicely to e to the negative x 1 minus x. And that's going to be 0 only when x is equal to 1, because e to the negative x is never 0. It gets close, but it's never equal to 0. Okay. So only one critical point. Okay. So let's test 2 and 0. Notice that I always try to test 0 because it's easy to plug in. Unfortunately, if 0 is one of my critical points, I can't do that. So let's see what happens. When I plug in 0, I get 0 plus 1, which is positive, so increasing. When I plug in 2, I get e to the negative 2 times 1 minus 2, which is negative 1, which is going to be negative, which implies that I'm decreasing. So for part 1, I'm increasing from negative infinity to 1 and decreasing from 1 to infinity. All right, moving on to the second derivative test. Let's see. I'm going to do product rule here, first times derivative of the second plus the second times the derivative of the first is going to give me a negative e to the negative x, because the first is negative x, so times the derivative of that is negative 1, okay, plus the derivative of e to the negative x, which is negative e to the negative x. All right, so let's clean things up a little. I pull out an e to the negative x and get x minus 1, x minus 2. All right. So, when is this equal to 0? Well, this is going to be equal to 0 only when x is 2. Oops. Right, because again, e to the negative x is never 0, but x minus 2 is 0 when x minus 2 is 0 when x equals 2. All right, so another number line. Possible point of interest. Let's try 3, and let's try 0. Okay. Don't forget to always be labeling what your number line is so that the reader or myself knows what you're talking about. So when I plug in 0, I get 1 times negative 2, which is negative, which implies concave down. When I plug in 3, I get e to the negative 3 times 1, which is positive, which implies concave up. So for the second part here, I'm concave down from negative infinity to 2, and concave up from 2 to infinity. And lastly, 3, there should be one point of interest, point of inflection at x equals 2, because that's where the concavity changed. Now, for the fun part, let's see what this graph looks like. So now I could tell you to graph something like this without a calculator. Okay. So 1 and 2 are where things are happening. There's 1, and there's 2. When I plug in 1, I get 1 over e. And that's a maximum value, or a relative value, a relative max. When I plug in 2, I get 2 over e to the 2, which is somewhere in here. And so that's where I have a point of inflection. So from here to here, I'm concave down. And here to here, I'm concave down. And I believe it does go through 0, 0. If I plug in 0, I get 0. And then from 2 to infinity, I have to be concave up, but also decreasing. Something like that.